AI coding agents are highly proficient at standing up back-end architecture. They can scaffold complex databases, map out server routes, and wire up APIs with incredible speed and structural precision. But when you ask that same agent to build the front-end user interface, that underlying logic often breaks down. The resulting interface is usually a mess of arbitrary padding variations, clashing color hex codes, and typography scales that jump randomly between sections. In development circles, this failure state is known as a Frankenstein UI. Without an overarching design constraint, the agent stitches together CSS rules that are statistically probable in isolation, but visually disconnected in execution. It destroys the user experience. This happens because of a core architectural limitation regarding how large language models handle visual design. LLMs possess deep semantic understanding of code, but they lack persistent spatial and aesthetic memory between individual prompts. During standard prompting, a single text request triggers a scatter chart of hundreds of disconnected CSS tokens. The AI must independently synthesize margin, padding, and color logic from scratch. This collapses into a disorganized trial and error process known as vibe coding. To achieve consistency, developers need a way to translate visual intent into the one format the agent handles with total precision: text-native constraints. Encoding aesthetic rules into a strict format allows the LLM to process design as pure logic, effectively simulating the spatial memory it lacks. The typical developer workflow involves manually overriding AI-generated Tailwind CSS classes, adjusting margins and colors line by line to force the layout into place. The friction hits when you ask the agent to add a new feature to that exact same page. It often overwrites those manual tweaks, reverting back to its original baseline. A common workaround is feeding a screenshot of a target brand UI into a vision language model to act as a direct reference. But vision models fail at precise replication. The model is measuring pixels by eye, rather than applying strict mathematical alignment. The visual input translates into non-standard code values, injecting classes like padding 5 or margin top 13 pixels that break a standard Tailwind spacing scale. Image recognition for UI generation is an exercise in visual guessing. It structurally fails to generate mathematically sound CSS grids. The next logical step is to eliminate the guessing by feeding a complete exported design system directly to the LLM. However, a standard Figma export is built as a deeply nested, complex node tree optimized for rendering software, not text processing. Dumping heavy JSON design schemas into a prompt incurs a significant context window penalty, creating a low signal-to-noise ratio. The LLM burns compute trying to map highly abstract, hierarchical JSON design tokens back to functional front-end DOM elements. This necessitates a zero-configuration design context that bypasses traditional visual design software completely. Complex, non-native data structures degrade an agent's ability to maintain strict token adherence during code generation. The architectural solution to this context problem is the Google Stitch DESIGN.md format. It is a concentrated plain text rulebook for your user interface. Where JSON schemas carry immense computational weight, raw markdown is lightweight and efficient. Because large language models are built as text prediction engines, they are proficient at parsing and adhering to markdown. A community repository called awesome-design-md curates elite brand design systems like Stripe, Vercel, and Linear, translated into this plain text format. Injecting a raw markdown constraint system aligns the visual design language with the structural format the LLM was originally trained on. A design.md file functions as a mathematical system. It takes the subjective feeling of a brand and translates it into rigid code parameters. Take the second section of the document structure, which dictates color palette and roles. Semantic roles like destructive action token prevent arbitrary hex codes for interaction states. In layout principles, an 8-point grid restricts the AI to approved Tailwind spacing. Typography roles set exact font families and letter spacing that map directly to rendered text. These structural constraints eliminate the need for the LLM to make any independent aesthetic decisions. Precise spatial and typographic text definitions force the agent to output deterministic, predictable CSS classes. The document also sets boundaries on what the AI must avoid in the design guardrail section. In advanced prompt engineering, defining negative constraints is critical for maintaining consistency. You can explicitly forbid the use of drop shadows or restrict maximum corner radiuses across the entire application. Defining these anti-patterns reduces the statistical probability of the AI generating off-brand visual elements. Instructing an agent on what not to do is a highly efficient method for protecting the integrity of a design system. Executing this workflow is a matter of dropping the design.md file into the root directory of a new project. From there, you prompt the agent to build a specific component based on that single root-level constraint file. The result is a complex, accurate UI component generated on the first pass, requiring 0 manual CSS overriding. This process removes subjective visual tweaking from the front-end development loop. Placing design constraints at the root of the project resets the agent's baseline behavior to be pixel-perfect and strictly token-compliant. There is a critical technical limit to this protocol that is necessary for maintaining engineering rigor. Providing plain text design rules does not replace the necessity of using complex, interactive UI libraries for highly functional components. A proper AI workflow uses the design document strictly for the visual layer, while a separate configuration file dictates the application logic. Bifurcating control between visual presentation and application behavior prevents the agent from conflating logic with layout. Adopting plain text design protocols shifts AI UI creation from an exercise in chaotic trial and error into an engineered deterministic system.